It will be presented by Professor Stan Tomov. He will be talking about heFFTe, highly efficient exascale FFT library for heterogeneous architectures. He received his MS degree in computer science from Sofia University in Bulgaria and a PhD in mathematics from Texas A&M. Currently, he's a research director in the Innovative Computing Lab and a research assistant professor in the EECS department at UTK. His research interests are in parallel algorithms, numerical analysis, HPC. Currently, his work is concentrated on the development of numerical linear algebra software, and in particular Magma, for the emerging architectures for HPC and heFFTe for FFT distributed computation. So let's give a big welcome to Professor Tom.
Thank you, DK, for the introduction and for inviting me here. It was very exciting to hear all the exciting work here on MPI. That's a little bit of a new topic for me, and I'm really happy to be able to collaborate on these topics. So that would be the title. Let's see. And we already heard the talk related to this topic from Alan Ayala. So some people from the team, they moved to other places. So this work is on FFT, and it's part of the DOE Exascale project. So this is ending now at the end of the year. So quite a few of the collaborators started going to industry, like Alan is at AMD, Azam had moved before to NVIDIA. We still continue collaborating with them. Miroslav Stoyanov, he's at Oak Ridge. And this was also in Jack Dungara's group. So Jack retired last year. He also received the Turing Award. So we are all very happy about this. And then we have many other collaborators, students and outside collaborators. This summer, for example, we had some collaborators from ETH Zurich. They needed one of those FFT libraries. So just to start, here is a hardware trend that just shows that computation and bandwidth, the communications are getting more expensive compared to computation. So this is over the years. We have different processors, and it is getting more and more expensive to communicate data. So in this case, you can see that we are at the case where really you need to reuse every number that you read, to reuse it about 100 times in order to be close to the peak. So anything less, for example, if you are doing a matrix vector product, every value is used once. So instead of 100 and close to the peak, if your code is organized in matrix vector products, you suddenly be getting just 1% of the peak of these machines. And this is what we have specialized in ICL. So this is the Magma library for density algebra. We always try to be close to the peak. So we try to get this data reuse and really remove communications. But as we will see in this FFT project, sometimes we just have to communicate. And then we have to come to the experts in MPI, because really that's a very important kernel, and it just turns out to be very communication bound. So just for completeness, what is mathematically the FFT? If you have a sequence of numbers, the FFT is just defined mathematically as a matrix vector product. So where the matrix is based of these frequencies of sines and cosines. So really, if you are going to compute it, it would be n square flops. It's just a matrix vector product. But of course, there are tricks in the FFT, where instead of these n-square flops, one can actually do it with n log n for the FFT. And then the inverse, actually this is orthogonal transformation, so the inverse is just the transpose. So, what we are really interested here to provide is multidimensional. So if we have, for example, a two-dimensional array, and if we want to compute the FFT of this two-dimensional array, mathematically, technically, we have to just do 1D FFTs of the columns in one direction, and then 1D FFTs in the other direction. And the order doesn't matter, but for performance, sometimes it matters how we choose this. And of interest are these three-dimensional FFTs. So based on this, the main building blocks of the FFT would be how to do those 1D FFTs. We will do them batched. And then there will be a lot of data reshuffles, because when you have a domain, and let's say it is split like this, one is like some data on one processor, really to compute this FFT efficiently, we will need all the data in one of these dimensions to be on the same processor. So they would first, all the processors have to communicate, send this data to one processor in one of the directions, then all of them would compute their 1D FFTs, and then we will do this for the other direction. So all these data transpositions actually are MPI all-to-all V type of communication. So the entire domain gets communicated. So, and then there are many applications that use this. So in cosmology, signal processing, image processing, deep learning now, molecular dynamics, particle simulations, PDE solvers, they all use these. And it is used because of the mathematics behind this. When you want to invert and solve a PDE technique, let's say some kind of Poisson problem, you take the Fourier transform on both sides, and then the differential operator actually can be taken out from the FFT as scaling coefficient. So in order to solve this PDE, basically one would just have to do one FFT, then scale, and then do the inverse FFT. So the cost is 2 FFT. It would be a cost of n log n, versus if you discretize this with a dense matrix, this operator, one would need n cube operation. So having this solved in n log time is very fast. It's basically the time just to write the solution. So it's as if you have the inverse almost directly, and you don't even do a matrix vector product with this. So it is very fast, and that's why it is used. This is also some example. It's used in compression, very important. So that's just MATLAB notation. So one would just take the FFT of some data, like an image, and then taking out some frequencies close to zero, making them zero, and then transferring again. One can see the image again recognizable. This is Fourier. So, and in this case, it's only 8% of the data are left, and still you can see that. So that's another application. Convolution also, convolution of two images. It can be expressed with FFT inverse, and then two FFTs and the dot product of the two images. That's also used in convolutional neural networks, for example, the basis. So we coded all this, and it is called heFFTe Library. So it has a lot of capabilities. So it handles multidimensional FFTs. The data, the input can be complex or real. All those versions that are required from any standard library in this. We have also different variations of these: discrete cosine, discrete sine transform. They have different types, convolutions. Many people would need batches of those, so these are all supported. And then also we support very flexible data layouts. As this was targeting exascale systems, we have been running on and that has been the target pre-exascale environment. So originally we were running on Summit mostly, now Frontier. We are still waiting for Aurora, but all these are now supported in heFFTe. So NVIDIA, AMD, and Intel GPUs, and also multi-core CPUs. And performance is very good. So Alan showed that we can actually do performance models. So this is a performance model based on the nodal bandwidth. So assuming that when you get more and more nodes, if we assume that the bandwidth would scale, then we can easily make a roofline model indicated by this line, as if we get peak bandwidth in and out of the node. And in those cases, sometimes we will get close to the peak, 90% of the peak. So, so it scales very well. Of course, there are problems that I will start coming to in a second. So ECP, they also wanted to define what was the state of those FFTs before the project started and what is now. So basically before there was not support for GPUs in distributed FFTs when we started. Now there are a few libraries that start supporting it. Some state-of-the-art library, they were just for CPUs at the time. So FFTW, for example, it was no longer at the time actively developed on these emerging platforms. Then there were some ECP applications that needed FFTs, but they had their codes fused in their framework. So really the idea was to get all those functionalities and make them available in a library for everybody and to support those exascale systems. So that's what we did, and we coded these with many versions. One interesting thing that happened is this is a profile of the CPU code, how typically FFT would run on those. So the red here is MPI communication. So on CPU-based system, it was typically half and half. You would do MPI communications and then some kind of these local computations, maybe data reshuffle. So, and with GPUs, when we accelerate it with GPUs, basically we can accelerate this part, and we almost shrank that to 0. And then it turned out that MPI is just communication. This cannot be accelerated, so this leaves to be 97% actually and more in MPI communication. So we just have to communicate, and any further improvements really are based on talking to MPI experts and trying to optimize certain parts in how we communicate. This is something more about the difference and how the project started. So as I mentioned, there were no GPU support before. Now we added this. Originally, we quickly coded something for the software engineering, following the LA pack, kind of scalar pack conventions. But then for convenience, to support all those different GPUs and growing code, we moved to C++. So now the heFFTe library is C++ library, and it heavily relies on the latest standards. And different backends are supported for the different GPUs. We have backends for the three main NVIDIA, AMD, and Intel GPUs. And then we support also multiple precisions. These are just some more experiences when we were preparing for these exascale systems. We were part of different projects within ECP. One was, for example, XSDK, had very useful conventions there that we had to comply with, and these were regarding configuring, installing. So heFFTe is totally compliant with those rules. It has spec installation, CMake installation also, and there are a bunch of other rules there. So also what help is collaboration with application developers, and then having also some supplemental fundings for different areas like mixed precision and batch support and things like that. Some of the current developments, to show how fast heFFTe is, we developed also a benchmark. So because it's memory bound, having a benchmark is also a good thing. Benchmark based on FFT is a good thing to measure also the quality of MPI libraries, the interconnect also on these systems. So we have a benchmark and we put there a number of libraries that were available at the time. This is just some columns here, what kind of data distributions they support. So basically, we try to cover all those needs that different application may need here with heFFTe. So, and most of the libraries that at the time were for CPU support. So these are many libraries on single device. So these are FFT libraries. We didn't try to develop those, although we have some in heFFTe. Basically, we use most of these as backend. So we can leverage any existing libraries by adding with the C++ interface backends. That's just benchmarking some of those libraries on different GPUs at the time, AMD, NVIDIA, and Intel, Power 9 also. This is the general algorithm. I already explained this. So we will have communications to send these into so-called pencils, these one-dimensional vectors to be on single processor. And then we will compute 1D FFTs in that direction. And then in this loop would go over the different dimensions. So we can do packing and unpacking also to try to speed up the MPI communications. That's again just a visualization of those procedures and all the functionalities that we support. So this is some of the scaling. So this is strong scaling taken on a size of 1020 cube. This is a typical size. These are just some distributions that we have, slabs or pencils in double precision, and this is single precision, and it's in time. So single is twice faster. What this graph shows is those slab decompositions are usually faster for because they communicate less for smaller amount of nodes, but then as we increase the number of nodes, the pencil become faster. And because of the strong scaling, at some point this stops scaling actually. So really one of the challenge now is to work with MPI people and try to improve this and where the scaling would stop. So this is some more scalability numbers. So this is weak scaling. Weak scaling, as the problem grows, we don't have problems, so it scales well. This is more about the roofline analysis. As I mentioned, we can theoretically compute what should be the performance, and we get very close to the roofline at some sizes, but of course these also deviate, so it's a matter of bringing more improvements there. That's more about the benchmark, so it's called heFFTe, and it's on GitHub. Compares all these libraries. These are just some performance numbers showing how these libraries compare. So this is on Summit nodes on the left. These are CPU on the left and GPUs on the right. And it is strong scaling, so at the end, as you can see, they all have this problem, which is typical for the strong scaling, and this is what we are trying to improve now. We have also some integration with tools, for example, tracing. We can trace the code, try to find problems. Integration with applications, so some applications heavily rely on FFT. Half of their time is, for example, spent on FFT. So when we accelerate this, we can get close to that percentage improvement of the overall code. Currently, we are running on Frontier a lot. So related to the performance models, that's just a comparison on Summit. The nodal bandwidth goes through 1 NIC, so it's just 25 gigabytes per second one direction, or 50 bidirectional. And theoretically on Frontier, it has 4 of these NICs, so it is 4 times higher, so one would expect to have 4 times better performance. And indeed, as shown here for weak scaling, we get this factor of 4 times and even more just because we have more bandwidth available. So this is the weak scaling. Strong scaling has more challenges, so I'm not showing it. So at this point, we are about to finish the project. So we have moved to a place where any further improvement just has to come with collaboration with experts in this area. So we work with the FFTe. As shown here, FFTe exceeds in performance even vendor optimized libraries for these systems. So these MPIs get optimized very well there still for the size that we need. As you can see, FFTe for small sizes, when we have the problems with strong scaling, gives much better results there. Also, what we do is parameterize. So and Alan showed us, so we have coded this in different ways. We can use all-to-all or all-to-all V, all-to-all W, point-to-point, different ways of blocking, non-blocking communications, grid size, and we have exposed this also to the user so that all these can be tuned. So in addition to other improvements, just having those versions, we can get some substantial improvements based on auto-tuning techniques. One interesting area now is to also look in this lossy or lossless compression at runtime. And DK Panda's team has a lot of work on this, so we still have to try it independently through the mixed precision efforts that ICL is trying. We did also some preliminary work. And as I mentioned, this summer we had a student, so they indeed have those applications where different solvers just solve with different accuracy. So in this case, they have this solver that would have accuracy of 10 to the minus 4. So in cases like this, of course, we don't want to overkill and do FFT in 64-bit precision. We can do different type of compressions and benefit from that. And what we played with is just casting, for example, to single precision to reduce the volume of communication, and we get, in cases like this, 2 times speed up. Of course, if this is integrated directly into MPI and we provide this interface, so we are suggesting an API for the interface for FFT where we can give accuracy, then this can directly give the user FFT with prescribed accuracy and as fast as possible. So, and finally, just to mention this grant that we received now, DK Panda is the PI, and it is with 4 institutions. So this is also with the University of Oregon, Samir, and Yifeng from San Diego Supercomputing Center and us. And the basic idea is to have this integration with MVPitch and Tau, and then to bring this to applications. And in this case, heFFTe is one of the applications. And this is looking into a number of innovations that are listed here, and we will try to bring those into these 2 applications. And I think that's the last slide, some acknowledgements. Thank you.
We have time for a few questions. Anybody here? Yes.
Thanks, Dr. Tomov, for your talk. So I have a question. So you showed that in, when we decompose the FFT and perform 1D FFT on local processors, what kind of operations are actually happening in that 1D FFT? Is it like some simple BLAS dot product or a MATWEC operation? The reason why I'm asking this is, say if I were to optimize some BLAS operations like MATWEC or a dot product, will it have an impact on the performance of 1D FFT?
Yeah, so typically we will have a batch of them. So mathematically it would be a matrix, which is the FFT matrix times a dense block. So mathematically would be a matrix multiplication, but because of the tricks of doing this in n log n time, actually the algorithm starts reducing it, so it's a sequence of data transpositions and then FFTs of size the factors where, let's say, if you do a FFT of a vector of 1,000, the typical algorithm would factorize this, like 1,000 would be like 2 times whatever the prime factors are, and then it would involve FFTs of that size plus data reshuffles. So So these would be the kernels, and they can, if you have them, they could be applied, but the vendors have done a lot of tricks into those codes. So internally, I don't know exactly how they code it, but performance, when we look performance, although this should be also memory bound because it is just done locally, but the GPUs have now 2000 gigabyte per second bandwidth and stuff like that. So it's actually runs as fast as DGEM, like a matrix product. So locally, they are very fast. That's why we make all the local computations almost zero cost. So then yeah, everything remains to be MPI.
Yeah. Thank you.
We have an online question from Raghu Reddy. Nice talk and impressive speed up. One confusing thing in what you mentioned is you get a significant fraction of roofline peak, but with almost 90% communication time, that seems difficult. Is the fraction of peak excluding communication?
The peak is considering entirely the communication. So the way we put the line for the peak, that is, one would be at that peak if computation was totally zero, ignored. So that's just the time for communicating and communicating at the theoretical peak. So maximum bandwidth of the devices at hand.
So like my question is, when you send out all-to-alls to convert the expenses to say like Y pencils, what could you overlap? Because typically these MPI libraries do like non-blocking, that they want to overlap some amount of compute. If it's communication, like can you overlap the local FFT that's already sitting there?
Yeah. So we could overlap things, but just because of the fact that it's less than 2%,
it's
it
2%,
will.
it's of no use.
So yeah, we stopped looking into that direction. But now that we look at compression, when we say, okay, so the GPU is not used, but maybe then we would use it for compression, I think then this would become relevant. So then we may actually try to overlap things, or then through tau counters, we can also tell the application actually that we don't need the GPU. So maybe the application would use it for something else, like maybe they can overlap with something. But yeah, for now, if it is just the FFT by itself, there is not so much to overlap. Yeah.
We have two more questions, Dr. Han and Kamal. Well, actually, I'm going to have a side chat with him.
I think my question is somewhat related to the question for the 97% communication time spent when you use GPU. That means GPUs are not being used well, right? Is that problem because of data distribution, or that's in general problem with the algorithm?
It's just because we have to wait for data. It is a fundamental algorithmic problem. We have to wait for data. Technically, the GPUs are used very efficiently. They're just used in those bursts of when they have to be used, and then they trigger this sending of data through MPI, and then they wait. So one idea that we discuss here, for example, would be, at least if we are not using them, maybe reduce the power to sound better to people. So if they are not used, at least not to consume power. The other is just to try to give it to applications through some indicators, maybe tau that we're not using it, maybe some other part of the code would use it, or if it's in a data center, if they get oversubscribed, can be used for something else. But it is just fundamental for the algorithm that communicates. So.
Okay. So yeah, what quick follow-ons? Is there anything in MPI that we can do to reduce that 97% to? Is there algorithm-specific optimization MPI can do?
I mean, these are the challenges. So that is actually the new grant which we got to actually carry out the research, how to optimize, do the core designing. Might be in the next few months, we'll have some solutions.
Okay, thank you.
Yeah. We are stuck now at this point, so it's...
Okay. So let's then give it thanks to Sven. Okay. So we'll move to the next one, our keynote talk for today. It will be presented by Bronis. Let's go to the next one. So let me introduce Bronis.